Welcome. Please enjoy this talk that I gave at VEHICULAR 2018. This talk is looking at whether or not errors in GPS position can affect routing protocols. Enjoy.
Hello, welcome, and thank you for attending this talk. I'm Justin Rohr, and I'll be presenting geographic centroid routing for vehicular networks. Just a little bit about us. I'm an assistant professor in computer science at the Naval Postgraduate School. I teach a number of classes in the computer networks area, including network modeling and analysis. I also lead the Center for Tactical Network Communication, and we work on a variety of projects in disruption-tolerant networking as well as network measurement in general. For those that aren't familiar with the Naval Postgraduate School, we are the Navy's research university, and we have about 1,500 graduate students, the majority of which are military officers and DoD civilians. We do not have any undergraduate students. Within the TANCAD lab, we have 3 professors and a couple of staff folks and work for a variety of organizations that you've probably heard of. Our focus is on network survivability and resilience, including disruption-tolerant networks for tactical environments. With this work, we have a couple of goals. One is to quantify the potential effects of GPS positional error on geolocation-based routing protocols. The other is to evaluate the effectiveness of a simple routing primitive designed to mitigate those effects. Note that among these goals is not creating the premier DTN routing protocol. We will leave that for future work. All right, a little background. So what do we mean by disruption tolerance? This is the ability of a system to tolerate disruptions in connectivity among its components. So this includes things like environmental challenges, channel fades, challenges due to mobility, delay, etc. So in order to accommodate these things from the routing protocol's perspective, we need to make local forwarding decisions without having globally consistent information, meaning we can't expect the routing protocol to converge. And the more information we have, the better decisions we can make. So it's increasingly common to try and input some sense of geolocation information into the DTN routing protocol in order to improve this decision making. So where does this information come from? GPS positional samples are coming from a piece of hardware that constantly updates the estimated position. But obviously, routing protocols are software applications, and so they will need to periodically sample this information and use those samples in their computations. So the per sample precision and accuracy can vary quite a bit. And there's lots of factors. Part of it is just the quality of the GPS receiver. How big is the antenna? How effective is it? You have a clear view of the sky and the horizon or not. But it is quite common to have cheap receivers with tiny embedded antennas, as well as a partially occluded view of the sky. So, how bad does that make it? Well, some days it can be really bad. I'm sure we've all seen the news articles about folks who blindly followed GPS directions and ended up in unexpected places. But to try and quantify that a little bit, the advertised error in GPS receivers is plus or minus 20 meters, and that's the intentional error that's added to the signals for civilian use. However, the error can be on the order of 1,000 meters, plus or minus 1,000 meters, but some prior work has shown that it's fairly common to have 100 or 200 meters of error, especially in urban environments. If we're talking about commercial GPS navigation devices that you've all used at one point or another, whether it's your phone or a dedicated device, there's a lot of post-processing that happens to the raw GPS samples. So they may do things like snapping to the nearest road, and basically they're presenting the best guess position to the user. Devices like smartphones also incorporate data from Wi-Fi access points and cellular radios into their position estimates. So all those innovations are driven by errors or limitations in using GPS position. But when we're talking about routing protocols, we probably don't have access to all of these additional sources of information. All right, now let's relate this a little bit to network simulators. When we're simulating DTN or mobile ad hoc network protocols, we traditionally get the position from the simulator as Cartesian coordinates. And it's the the raw position that the simulator is emulating for the node, and that location is accurate to an arbitrary precision. And these are the conditions under which geographic routing protocols are typically designed and tested, because mobile test beds are fairly hard to implement and operate. So that means that we're designing these protocols around perfectly precise geo-coordinates. And we include ourselves in this indictment. Our own prior work makes these sorts of assumptions. The question is, what if we introduce error into the simulation reported locations to make it more realistic? We'll come back to that question in a minute. We're going to talk about a couple of routing protocols that we've designed to potentially mitigate these effects. So first, the primitive. We call it the centroid, and it's designed to be simple and as a building block that can be combined with other techniques for more advanced protocols. So it's essentially the average node position over time. And every so often, at a fixed interval, the node will update the centroid with its current position and incorporate that into the running average. So if you want to think of this pictorially, the centroid is kind of the center of mass of the 2D area or 3D area through which the node has been moving. So the more time it spends in one area, the closer the centroid will migrate to that area. So using this to form a protocol, first we go for the simplest case. So we have the centroid routing protocol, which is an epidemic-based protocol. It's multi-copy, introduced in this work, and the nodes at each encounter exchange both their centroid and the list of messages currently in their buffer. They then limit the number of messages they'll copy based on the distance between their centroid and their neighbor's centroid. So for neighbors with distant centroids, they will copy more messages. This is very comparable to the vector routing protocol, both in complexity and design. And the idea is to improve efficiency by reducing the number of messages copied to nodes with similar centroids. So the assumption is if a node has a similar centroid to the current node, so the neighbor and the current node have similar centroids, they are both likely to encounter the same nodes. So it doesn't make sense for them to both carry copies of this message. However, nodes with distant centroids are likely to encounter different nodes than the current nodes, and so it does make sense to copy messages to that node. The center mass router builds on the same routing primitive and uses the centroid protocol as its base. In this case, nodes record the centroid and timestamp of all encountered nodes. So they maintain a list of this information. And they exchange this list with each neighbor when they exchange message lists. And these are then merged into their own local centroid list. Over time, the list of all node centroids will propagate throughout the network. The copying is similar in that more messages are copied to nodes with distant centroids. However, it's further limited in that messages are only copied to neighbors with centroids that are closer to the destination than the current node's centroid. So this limits the flow of messages in directions away from the destination. So let's review some results. For this work, we are using the one simulator. It's quite common for DTN protocol simulations. And we use the provided mobility and traffic scenario. That's the default Helsinki scenario, which is also quite common due to its being the default in this simulator. That scenario includes pedestrians and cars and trams as the mobile nodes in its environment. And it has a number of properties. Those are detailed in the paper in terms of what the buffer sizes are and the radio properties for those different nodes. And it's a map-based mobility model. So in this work, we're not targeting a specific mobility model. This one includes a variety of mobility with the different node capabilities and speeds. And so it should provide a good baseline comparison. So first we want to look at the effects of positional sample error. The idea being to find out if this even matters, right? Do the potential errors in GPS make a difference? So for this, we are just going to look at a couple of protocols, right? So we have the vector protocol that's flooding based, and it extrapolates trajectory from the position history. So it's doing a more precise calculation in terms of it's trying to determine the direction that the node and its contacts are headed in. And it will limit limit message replication if the nodes have similar trajectories. So you can see a parallel there to what we did with Centroid. The simulator itself does not add noise to its position, so we make a variant of each of the routing protocols that when it gets the position from the simulator, it adds random noise before it uses that sample. So it's adding random noise uniformly distributed plus or minus 20 meters along each axis. So this is much smaller than what we said that typical noise might be in urban environments, right? We said that could be 1 to 200 meters. So we're taking a conservative estimate of that noise. And here we see some results. So we're looking at the packet delivery ratio, which in this case is also the message delivery ratio. Messages and packets are equivalent in the one simulator. Looking at this with respect to the transmit speed. So as we increase the transmit speed, we see that the packet delivery ratio increases. So the different routing protocols are able to make use of this additional resource up to a certain point where it levels off. And looking at the relative performance, we see that the center mass router and the center mass router with noise are virtually indistinguishable from one another. Right? So there's no statistically significant reduction in performance with the addition of GPS errors to that protocol. Likewise with Centroid, those curves again are right on top of one another, and so we see little to no difference when noise enters the picture. However, when we look at Vector, right, aside from the fact that it performs worse than the other two protocols, we also see that the version of Vector with noise is a non-trivial amount lower. So the addition of noise to that protocol does negatively impact it. Let's look at the performance in terms of overhead. For each of these buffer sizes, the overhead is the same between Centroid and Centroid with noise, and center mass with noise. However, with Vector and the addition of GPS error, so Vector with noise, the overhead increases. So not only did performance decrease, but the overhead ratio increased. This is the overhead due to the number of copies of each message being circulated through the network relative to the number delivered. We can also look at the overhead with respect to the transmit speed and see that the overhead is increasing dramatically as Vector and Vector with noise get more and more resources. So the more they're able to transmit, the more overhead they have. Now there is some increase for Centroid as well. Center mass is almost flat, but the increase is much more constrained than in the Vector case. All right, so from those first results, we can see that, yes, there is something to this, right? Depending on how a protocol makes use of geolocation information, it does negatively impact the performance of that protocol. And so it is possible to then design a primitive that's relatively immune to this. So then the question is, how do these Centroid-based protocols compare to the state of the art, right? So Vector is not a particularly sophisticated protocol, so we don't want to treat that as our only comparison point. And so we're including protocols that don't even make use of geographic information. They're just recognized as DTN protocols that perform well. So these include MaxProp and Rapid and Prophet version 2, as well as a couple of our own previously proposed protocols. In these results, we also show the performance of an Oracle router just to see what our benchmark is. So looking at the packet delivery ratio with respect to transmit speed again, same scenario, but with a full set of unmodified protocols, we see that our own protocol Gapper is the closest performing to the Oracle at higher transmit speeds. MaxProp does well also at lower transmit speeds, but has this weird behavior of actually doing worse as transmit speeds increase. Then we have a Gapper version 2 protocol, right? But the two protocols that we're really interested here, Centroid and CenterMass, are kind of below the midpoint relative to the other protocols, right? So kind of middle of the pack, not the worst, but not the best either. They are outperforming Vector and Prophet version 2. Likewise, when we look at this with respect to buffer size, we see that some of the protocols with relatively unconstrained buffers are able to achieve nearly the performance of the Oracle, right? Those include Gapper, MaxProp, and Rapid, and Vector. whereas the R2 protocols don't fare nearly so well. They plateau at a much lower buffer size and don't really see additional benefits as the buffer size is enlarged. So not looking great there until we get to overhead. So overhead is a bit of a different case, where we see that the centroid and center mass bars are barely showing and don't particularly change as the buffer size is increased, whereas some of the other protocols are orders of magnitude higher in terms of overhead. So if you're concerned about overhead, then these protocols are definitely of interest. Of course, overhead being message copies, that translates directly to power consumption and reduced battery life and so forth. So looking at the overhead ratio with respect to transmit speed, we see that actually some of these protocols have exponentially increasing overhead as the transmit speed increases, whereas centroid and center mass and gapper version 2 are quite low, and they do increase somewhat, particularly gapper version 2, but they do not appear to have the exponential increase that some of the other protocols do. We decided that wasn't especially convenient, having to look at a few different metrics and say, well, it's good on one, but not so good on the others. So we wanted to combine those into one metric for comparing the protocols, and we call this protocol efficacy. And this basically relates the delivery ratio to overhead, right? So we capture this trade-off between the packet delivery ratio and the message copy overhead, and this allows for some single value comparison of the protocols. So by this measure, we can see that center mass clearly outperforms centroid, right? So it had a higher delivery ratio, it had a lower overhead. We've captured this in one metric. Centroid comes in second because it is still remarkably efficient in terms of low overhead, and then it's relatively closely followed by Gapper 2. And if you remember back to earlier slides, Gapper 2 had a bit higher performance than either of these protocols. The rest of the group, then, in terms of efficacy, are quite low, and this is because of their relatively high overhead. This is in terms of the buffer size. We see the same pattern holding true with respect to the transmit speed, and see that there's even a couple of cases on the lower end where Gapper version 2 outperforms centroid in terms of efficacy. It's worth noting the relationship between the centroid distances that's used as the primary limiter in terms of how many messages are copied in centroid and center mass could certainly be tuned. So we could trade off some of the overhead, so allow more copies, in order to gain message delivery. And this is a point that we'll consider in future work. All right, a couple of takeaways. One is that, yes, GPS sample error can significantly impact routing performance. It all depends on how those samples are being used, and so we're able to use them carefully in a way that they do not impact performance in centroid and center mass. And our new metric efficacy is a helpful metric for doing protocol comparisons to capture the relationship between packet delivery ratio and overhead.